The silence is not an absence, but a presence. It is a thing shaped by epochs, a palpable stillness that settles over the rust-colored plains in the long, slow hours before the sun breaches the horizon. This silence has a weight, a texture. It is the auditory signature of a world where no breath is drawn, no leaf rustles, no heart beats in the deep places. It is a silence of profound and ancient making, a testament to processes that operate on timescales that dwarf human history, governed by the patient, relentless logic of physics in a near vacuum. This Martian dawn silence is broken only by the most ephemeral of sounds, the whisper of a thin, cold wind as it snakes across the regolith, a sound like escaping gas, carrying with it the finest particles of dust, the ground-up remains of mountains that have stood for billions of years. And then another sound, foreign yet deliberate, the gentle, methodical crunch of robotic wheels upon that same regolith. A sound of careful progress, of measured force, a punctuation mark in the endless sentence of geologic time. This is the sound of a visitor, a machine built by beings from a world saturated with noise and life, now listening intently to the quiet of a world that is not dead but sleeping, a sleep so deep it mirrors death. This stillness is not merely a condition of the present. It is the culmination of a biography, the final state in a narrative of catastrophic change. It has reigned in its current form for billions of years, a span so vast it crumples our intuitive grasp of history. To comprehend a billion years is to attempt to hold the ocean in one's hands. Within that span, our own species has existed for less than a heartbeat, our civilizations for less than the blink of an eye. And yet, for all but the most recent fragment of that cosmic eternity, this silence was not absolute. The wind was thicker, warmer, carrying the scent of water. The sounds were of a different character. The lap of waves against a rocky shore, the patter of rain on volcanic plains, the distant rumble of tectonic forces that have long since stilled. The silence we perceive today is the silence after the conversation has ended, after the orchestra has departed, leaving only the empty hall and the memory of the music. It is the quiet of a room where great and momentous events once transpired, now frozen in a perpetual state of aftermath. The world that presents itself to the robotic visitor is one of magnificent desolation. The term magnificent speaks to the scale, the grandeur, the sheer audacity of the geology, canyons that could swallow continents, volcanoes that pierce the sky, dunes that stretch in perfect, undulating waves towards an impossibly distant horizon. Desolation speaks to the emptiness, the lack of the vivifying principle that, on our own world, turns rock and gas into forest and meadow, into the teeming, chaotic, glorious struggle we call a biosphere. Here, the panorama is one of dust and rock in infinite variation, a study in ochre, umber, and crimson, stretching towards a horizon that has borne witness to the most profound of losses, the death of an ocean. That horizon is not merely a line where sky meets land, it is a monument to evaporation and escape, a tombstone for a body of water that may have once contained more volume than our own Arctic Ocean. It is a line that has seen the slow retreat of hope, the relentless draining away of a world's potential, leaving behind only chemical ghosts in the rocks and the hollowed-out riverbeds that wind like scars across the face of the planet. Yet, within this seemingly sterile expanse, within a landscape that appears, to all our senses and most of our instruments, to be a monument to inorganic processes, A secret may have been slumbering. Not a secret hidden in a vault or encoded in a language, but one imprisoned in the very fabric of the planet itself, in the atomic relationships between elements, in the crystalline lattices of minerals, in the subtle telling arrangements of matter that whisper of a different kind of process. This secret resides within a single, unassuming stone no larger than a human hand, a fragment of mudstone that, to a passing orbital eye or a rover's panoramic camera, is indistinguishable from a billion others. It is a nondescript piece of a world's shattered history, a page torn from a chronicle of which we have no index. But within its fine-grained matrix, within the spaces between clay platelets that settled from quiet water unimaginable ages ago, a narrative may be locked away. A narrative that whispers not of geology, not of volcanism or impact or Aeolian erosion, but of genesis. It hints at the possibility of a transition, a crossing of the ultimate threshold, where the predictable, if complex, dance of chemistry became something else, something persistent, something that could harness energy, grow, and replicate. It is a potential answer, or the first fragment of an answer, to the oldest question humanity has ever dared to ask the cosmos. A question we have posed to the stars in myth, in religion, in philosophy, and now in science: are we alone? This inquiry is not merely a story of scientific discovery, though it is that in its most refined and ambitious form, it is, more fundamentally, a detective story of cosmic proportions. The crime, if one can call it that, is the act of creation itself, the origin of life. The scene is a planet, Mars, that is not a random celestial body, but a sibling to our own, born from the same stellar nursery, shaped by similar forces in the early solar system. It is a mirror, albeit a dust-covered and fractured one, in which we might finally see our own origins reflected, not in the mythic sense of a deity's breath, but in the physical, chemical, and potentially biological sense of a natural process unfolding under a different sky. The timeline of this investigation spans 4.5 billion years, reaching back to the solar system's tumultuous infancy. The evidence is circumstantial, buried, altered by time, and exquisitely subtle. The suspects are not persons, but processes, biological on one hand, abiotic on the other. And the detectives are a global consortium of scientists, engineers, and dreamers, using tools of remote sensing, robotic manipulation, and analytical chemistry to interrogate a world that cannot speak, but may have left a record in stone. This is a narrative woven from the most resilient and intricate of threads. The thread of chemistry, which describes the interactions of atoms and molecules, the formation and breaking of bonds, the flow of energy that is the currency of all change. The thread of time, the fourth dimension through which the story unfolds, a dimension that allows for the accumulation of chance, for the slow winnowing of possibilities, for the patient work of entropy and of occasional glorious negentropy. The thread of hope, that most human of motivators, which drives us to look beyond the next mountain, beyond the next ocean, beyond the next planet. And the counterbalancing thread of rigorous skepticism, the disciplined unwillingness to believe what we wish to be true, the commitment to allowing nature to reveal its truths on its own terms, even if those terms disappoint our deepest yearning. It is a quest that pushes the very boundaries of our understanding of what life is, demanding we define the undefinable of where it can take root, forcing us to expand our concept of habitabilities to include dark, cold and radioactive realms, and of what it means for a universe born in fire and expanding into cold darkness to become aware of itself through us and perhaps through other minds gazing back from the deep. What we are about to explore through the lens of this discovery is a single point of data. In the vast database of the cosmos, it is a single entry, a collection of enigmatic spots on a rock, a specific spectral signature, a particular ratio of elements in a minuscule grain. It is easy to dismiss a single point, but in science, as in navigation, a single, well-defined point, when viewed from the proper perspective, can anchor an entire universe of speculation. From this point, this seemingly insignificant anomaly in a Martian mudstone, endless lines of inquiry radiate outward. They lead us backward into the deep past of our solar system, to a time when Earth and Mars were both newborn, wet, and bombarded from space. A time when the ingredients for life were being delivered and mixed in planetary-scale cauldrons. They lead us inward into the fundamental principles of biology, into the question of whether the logic of life is a universal logic or a parochial twist of fate on our own world. And they lead us forward into a future where our place in the cosmos may be forever redefined, where the philosophical and practical implications of knowing we are not alone will reshape human culture, ambition, and identity. To comprehend the full weight of this moment, the profound significance of this particular rock in this particular crater, we must first perform an act of temporal and imaginative translation. We must step back, not just in space, but in time, and behold Mars not as it is, a frozen desert world, but as it was. We must reconstruct its lost vitality, its faded blueprints. Imagine, if you will, a different world entirely. Not a sibling in its current decrepitude, but a twin in its prime. A young Mars, vibrant and dynamic, cradled in the early, faint light of a younger sun. That sun, our sun, was only about 70% as luminous as it is today, a cooler, smaller disk in the sky. Yet, beneath its gentle rays, Mars thrived. Its skies were not the thin, tenuous veil of today, but a thicker atmosphere, dense with carbon dioxide, nitrogen, and water vapor, tinged perhaps with the haze of photochemical smog or the faint blush of dust suspended in a more active hydrological cycle. This atmosphere was not just a blanket, it was a shield, a thermal regulator, and a chemical reservoir. Beneath this sky lay not a global desert, but the shimmering, reflective expanse of a northern ocean. Orbital topography tells this tale unequivocally. The vast, flat lowlands of the northern hemisphere, lying kilometers below the rugged southern highlands, conform to what is expected of an ancient seafloor. Its proposed shorelines, though debated, trace sinuous paths that could mark the boundary between land and water. This was not a temporary puddle, but a persistent feature, potentially lasting for hundreds of millions of years. And feeding this ocean was a planet-wide circulatory system. River valleys, some dwarfing the grandest canyons on Earth, snake across the Martian surface. These are not the sharp, dry gullies carved by sudden floods, though those exist too, but valleys with meandering paths, with tributary networks, with features that speak of persistent, stable flow over immense periods. They are the ghosts of rivers that carried water, and more importantly, sediment from the highlands down to the lowlands, feeding into deltas that fanned out where these waterways met the standing body of the ocean. The Jezero crater, Today, a dry, wind-scoured and spectacularly desolate basin was one such haven. It was a lake. A crater lake, its circular walls forming a natural basin, fed by a river channel that breached its rim. That river carried not just water, but a cargo of eroded material from the surrounding highlands, clays, sulfates, fine silts, and perhaps organic molecules forged in the atmosphere or delivered by comets. Where this river met the quieter waters of the lake, its velocity dropped and its sedimentary burden settled out. This created a delta, a fan-shaped deposit that is the geological equivalent of a history book, its layers preserving, in fine grain and chemical subtlety, a record of the water's flow, the climate's rhythm, and just possibly the presence of inhabitants. The waters of Jezero were likely placid, a stable environment for thousands, perhaps millions of years. Its shores, its sediments, its chemical gradients between the inflowing river water and the lake water, between the sunlit surface and the anoxic depths, would have been a potential haven for the complex chemical dances that precede biology. It offered the three fundamental requirements: a solvent, liquid water, a source of energy, sunlight or chemical disequilibrium, and the necessary building blocks, the elements of life: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, and others. This was a world not just with water, but with a protective magnetic field. Deep within its core, a dynamo of molten iron and nickel churned, generating a planetary magnetic field that reached out into space, deflecting and shaping the solar wind, a relentless stream of charged particles from the sun. This magnetic shield was a guardian of the atmosphere, preventing the solar wind from stripping it away atom by atom, and a protector of the surface, deflecting harmful cosmic and solar radiation that could break apart complex molecules. It was a world with active volcanism, as evidenced by the towering peaks of Olympus Mons and the vast Tharsis Bulge. These volcanoes were not just geological features, they were planetary engines. They spewed forth not just rock and ash, but the volatile gases, water vapor, carbon dioxide, sulfur dioxide, that replenished and thickened the atmosphere. They brought heat to the surface and subsurface, driving hydrothermal systems where hot water interacted with rock, creating environments rich in chemical energy and mineral diversity, environments that on Earth are cradles for vibrant microbial ecosystems. For perhaps 1 billion years, this was Mars, a wet world, a temperate world, a dynamic world. A world that, by every metric we have derived from our intensive study of our own planet's infancy, was habitable. The term habitable is carefully chosen. It does not mean inhabited. It means capable of supporting life, given the right spark. It describes a set of environmental conditions: liquid water, chemical energy, essential elements, stability over time, that are consistent with the known requirements of life as we understand it. Earth, in its first billion years, was also a violent, turbulent place, subject to intense bombardment and a poisonous, oxygen-free atmosphere. Yet, within that chaos, life emerged with what appears, in geological hindsight, to be astonishing rapidity. The transition from a merely habitable world to an inhabited one is, without exaggeration, the greatest gulf in all of nature. It is the leap from the deterministic, if complex, realm of physics and chemistry into the emergent, teleonomic, self-sustaining, and replicating complexity of biology. It is the moment when matter organizes itself not just into intricate structures, but into structures that can maintain their organization against entropy, that can extract energy from their surroundings to fuel that maintenance, and that can make copies of themselves with variations, thereby entering the arena of evolution by natural selection. On Earth, we know this leap occurred, and the evidence suggests it did so with a speed that is either deeply puzzling or profoundly revealing. The oldest known rocks on Earth, the Acasta gneiss in Canada, are about 4 billion years old. But the first unambiguous fossil evidence of life, stromatolites formed by photosynthetic bacteria, dates to about 3.5 billion years ago. More controversial, but highly suggestive, chemical signatures in even older rocks in Greenland and Australia hint at biological activity as early as 3.8 billion years ago. Considering that Earth's surface was likely too molten and bombarded to be stable before about 4.4 billion years ago, this suggests life arose within the first few 100 million years of the planet's existence, where liquid water was present. This rapid emergence poses a critical question. Is this a staggering statistical fluke, a miracle of circumstance so unlikely that it may have happened only once in the observable universe? Or is it an indication that, given the right conditions, the conditions of a wet, rocky planet with chemical energy sources, the genesis of life is not a miracle at all, but a natural, even probable, consequence of planetary evolution? Is the universe, in its fundamental laws, biophilic? This is the central, throbbing enigma that Mars presents to us. It shared those right conditions. It had the water, perhaps in greater global abundance in its early history than Earth. It had the energy sources, sunlight on its surface, chemical disequilibrium at water-rock interfaces, likely hydrothermal systems. It had the chemical building blocks delivered by the same comets and asteroids that seeded Earth. And crucially, it had the time. The window of surface habitability on Mars may have been open for 1 billion years, a duration more than sufficient for life to emerge on our own world. So the question burns with an intensity that fuels decades of exploration. Did the spark ignite? Did the silent, sterile chemistry of its ancient lakes, its hydrothermal vents, its subsurface aquifers ever cross that imperceptible, momentous threshold into something we would call alive? The quest to answer this is the raison d'être for our most sophisticated missions to Mars. We do not go merely to find water, though that confirms habitability. We do not go merely to map its geology, though that provides context. We go to search for a second genesis, a data point of incalculable value, a single, confirmed instance of life originating independently of Earth would transform the unknown factor in the cosmic equation from a question mark into a number, and that number would tell us whether we are a cosmic accident or a cosmic imperative. Our emissary in this existential search is not a human, not yet, but a machine of exquisite complexity and quiet perseverance. In February of 2021, amidst a global pandemic that tested humanity's own biological resilience, a technological marvel named Perseverance completed its 7-month journey from Earth. The Rover, a robotic geologist the size of a small automobile, encapsulated within a protective aeroshell, slammed into the thin Martian atmosphere at over 12,000 miles per hour. What followed was a sequence of maneuvers of breathtaking, autonomous precision, the entry, descent, and landing profile that its engineers, with characteristic understatement, dubbed 7 minutes of terror. A heat shield glowed at thousands of degrees, dissipating kinetic energy, a supersonic parachute, the largest ever deployed on another planet, billowed open at precisely the right moment. Radar locked onto the approaching surface, and in the final moments, a rocket-powered descent stage fired, slowing the craft to a hover. Then, the final magic trick, the sky crane maneuver. The descent stage lowered the rover on cables like a spider on a thread, placing its 6 wheels gently on the rust-colored regolith before cutting the lines and flying away to crash at a safe distance. It was a ballet of physics and engineering, a testament to human ingenuity, and it came to rest on the very floor of that ancient lakebed, the Jezero crater. The circle was closed. A machine built by a life-bearing world had arrived to search for signs of life on a world that may have once borne it. Its mission, born from decades of orbital reconnaissance by craft like Mars Reconnaissance Orbiter and the hard-won lessons of its predecessors, Sojourner, Spirit, Opportunity, and Curiosity, was unequivocal: to seek signs of ancient microbial life. But Perseverance is not merely a set of eyes, a remote camera. It is a mobile, autonomous analytical laboratory, a field geologist with a suite of instruments more capable than any that have come before. Its robotic arm is a marvel of dexterity, ending in a turret that is in effect a complete geochemical toolkit. Among its most critical instruments is Pixel, the planetary instrument for X-ray lithochemistry. Pixel is an X-ray fluorescence spectrometer. When placed close to a rock, it fires a narrow beam of X-rays that knock electrons from the atoms in the rock. As those atoms stabilize, they emit secondary X-rays of characteristic energies, a unique fingerprint for each element. By scanning its beam in a fine grid, Pixel can map the elemental composition of a rock with a spatial resolution finer than a grain of salt, revealing the distribution of iron, silicon, sulfur, phosphorus, carbon, and dozens of other elements. It sees not just what a rock is made of, but how those ingredients are arranged, revealing textures and associations invisible to the naked eye. Alongside Pixel sits Sherlock, an instrument with a name that is both an acronym and a nod to the detective work it performs. Scanning habitable environments with Raman and luminescence for organics and chemicals. Sherlock employs a fundamentally different technique. It uses a deep ultraviolet laser to shine on a target. When the laser light interacts with molecules, most of it is scattered elastically, the same energy as the incoming light. This is Rayleigh scattering, but a tiny fraction undergoes inelastic scattering, shifting to a different wavelength. This is Raman scattering. The amount of this shift is determined by the vibrational modes of the chemical bonds within the molecules. Like plucking a guitar string, each bond produces a specific note, a spectral peak that is a direct fingerprint of that molecule's structure. Sherlock's spectrometer collects this scattered light, allowing it to identify specific mineral phases and, most importantly, organic compounds, the carbon-based molecules that are the essential scaffolds of life as we know it. Sherlock can also detect luminescence, the light some organics emit when excited by the UV laser, providing another layer of identification. Together, Pixel and Sherlock form a partnership of unparalleled power. One tells you where the elements are, the other tells you how those elements are bonded into molecules. They allow the rover to not just look at rocks, but to read them, to decipher their chemical histories, to find the subtle text in the stone that might say, "Life was here." For years, Perseverance has been a tireless explorer, traversing the crater floor, climbing onto the delta deposits, drilling core samples, analyzing layer after layer, building a meticulous geological history of Jezero. It confirmed the presence of clay minerals, phyllosilicates, that form in the presence of neutral, life-friendly water. It mapped the stratigraphy of the delta, identifying the coarse-grained channel deposits of the ancient river and the fine-grained horizontal layers of the quieter lake bottom, the very sediments that would have settled quietly, potentially entombing any microscopic inhabitants in a protective tomb of mud. The rover was building a case, establishing the environmental context for habitability. Then, in the Martian summer of 2024, while investigating the margins of the Neretva Vallis, a river channel that once carved through the crater rim to feed the lake, its instruments turned their gaze upon a particular slab of fine-grained mudstone from the Bright Angel Formation. To the panoramic cameras, NavCam and MastCam Z, it was another rock among millions, a weathered slab of greyish stone. But to Pixel and Sherlock, it told a story written in a different language. The rock, which the mission scientists later gave the evocative and earthly name Chihuahua Falls, was identified as a sedimentary deposit. Not a volcanic basalt, not an impact breccia, but a mudstone. This is critical. Mudstone is the product of the finest sediments, clay and silt particles settling out of still water. On Earth, such fine-grained sedimentary rocks are premier preservers of biosignatures. Their low permeability seals out oxygen and other degradative agents, and the clay minerals themselves have charged surfaces that can adsorb and protect delicate organic molecules and even the shapes of microbial cells for billions of years. This was the perfect geological library for a potential biological record. Within this matrix, Sherlock detected the unmistakable molecular fingerprints of organic compounds, not just simple carbon chains, but more complex, ring-like structures, suggestive of aromatic compounds, mapped an enrichment of key elements associated with life's machinery. Carbon, of course, but also phosphorus, a central component of genetic material and energy-carrying molecules like ATP, as well as iron and sulfur, which play crucial roles in metabolic pathways, especially in anoxic environments. But the most tantalizing discovery, the one that set pulses racing in science team meetings, was one of morphology, of shape and pattern. Embedded in the mudstone were tiny distinct spots. They came in two types. Some, nicknamed leopard spots by the science team, consisted of a light-colored center surrounded by a distinct, sharp, dark rim, their diameters ranging from 200 micrometers, about the width of a human hair, to a full millimeter. Others, smaller and more numerous, were dubbed poppy seeds, dark specks scattered across the surface. To the untrained eye, they are inconsequential blemishes, mineralogical freckles of no import. To an astrobiologist, a geobiologist, they are a siren call, a visual pattern that triggers deep-seated recognition. For pattern is the language of biology. Randomness is the language of pure geology. The ordered, concentric, boundary-defined nature of these spots whispered of organization, of a process that acted from a point and propagated outward. The chemical analysis from Pixel revealed the critical telling pattern. The dark rims of the leopard spots were significantly enriched in iron and phosphorus compared to both the surrounding rock matrix and the lighter centers of the spots themselves. This is not a random or homogeneous distribution. It is a specific, localized chemical pattern, a gradient. The iron and phosphorus are concentrated at a boundary, a frontier. This specific architecture, a depletion zone in the center, an enrichment at a sharp rim, pointed the minds of the researchers, steeped in the study of Earth's earliest life, toward a phenomenon well documented in the fossil record and in modern environments. Microbial iron reduction. It was a pattern that looked like a fossilized chemical signature of a microbial colony's activity. To understand why this is so profoundly provocative, we must descend from the planetary scale to the microscopic, from the red plains of Mars to the hidden dark economies of the microbial world on our own planet. We must venture into environments devoid of oxygen, such as the deep anoxic layers of lake sediments, underground aquifers, or the subsurface beneath the seafloor. In these realms, where the familiar metabolic pathway of aerobic respiration is impossible, life has evolved remarkable and diverse alternative strategies. Among the most ancient and widespread of these is the ability to breathe not oxygen, but metals. Certain bacteria and archaea, some of the most primitive lineages in the tree of life, have perfected this art. One of the most common of these processes is the reduction of iron. Microbes like Geobacter and Shewanella species take in oxidized iron, known in its ferric state as iron ferrate, which is insoluble and forms rusty-colored minerals. They use this iron as a terminal electron acceptor in their respiration chain. In doing so, they reduce it to ferrous iron, or iron-on, which is more soluble and is expelled as a metabolic waste product. This process, called dissimilatory iron reduction, is a form of chemosynthesis. It releases chemical energy that the microbe harnesses to power its cellular functions, to build proteins, replicate its DNA, maintain its membrane potential. Life here derives its energy not from the distant sun, but from the chemical disequilibrium right in the rocks it inhabits. It is a deeply intimate relationship between biology and geology. The consequence of this metabolic activity is not invisible. When this microglia produced, soluble ferrous iron diffuses away from the cell and encounters other dissolved ions like phosphate, it can precipitate out as new minerals. A common product is vivianite, an iron phosphate mineral. The microbial activity creates a focused chemical microenvironment, a tiny engine of reduction. As a colony grows, it can create a propagating front of iron reduction. This often leads to the formation of distinctive mineralogical textures that mirror the colonies themselves: concentric rings, condyles, spherulites, and yes, spots with distinct rims where the reduction front has moved through the sediment, leaving behind a halo of reduced iron and phosphate minerals. On Earth, such textures, when found in ancient rocks, are considered potential biosignatures, indicators of past microbial life. Simultaneously, the Sherlock instrument detected spectral signatures highly suggestive of another mineral, graphite, an iron sulfide. This mineral, too, has a powerful biological connection on Earth. Graphite is often formed through the metabolic activity of a different class of microorganisms, sulfate reducers. In oxygen-poor environments, rich in sulfate, a common component of ancient waters, these organisms break down sulfate ions, reducing them to sulfide. This sulfide ion is highly reactive and readily combines with iron to precipitate as iron sulfide minerals. The initial precipitate is often a poorly crystalline form like graphite, which can later transform into the more stable pyrite, known as fool's gold. These precipitates frequently form distinctive rhomboidal clusters, microscopic, raspberry-like spheres of iron sulfide crystals that are considered strong potential biosignatures in Earth's oldest rocks. Here, in this one Martian mudstone, the chemical and mineralogical clues were aligning into a narrative that was hauntingly, compellingly familiar. Organic carbon, the backbone. A mineral assemblage suggestive of two classic anaerobic microbial metabolisms, iron reduction and sulfate reduction. A physical texture, concentric spots with chemical gradients indicating localized focused chemical activity. On our home planet, faced with such a confluence of evidence in an ancient sedimentary rock, the conclusion would be strongly, though always cautiously, pointed towards a biological origin. The null hypothesis would be under severe strain. But Mars is not Earth, and the noble, disciplined pursuit of science requires not confirmation of what we hope to find, but relentless, almost adversarial skepticism. It demands that we try to prove ourselves wrong. Thus began the most crucial intellectual phase of the discovery, the systematic, rigorous attempt to murder the hypothesis. The scientific paper detailing the findings, published after months of internal review and debate, did not begin with a bold declaration of alien life. It began with the establishment of a null hypothesis. These features, these chemical patterns, were formed by abiotic, purely geochemical processes with no biological involvement whatsoever. The team's solemn task was to try, with all the tools of geochemistry, mineralogy, and comparative planetology at their disposal, to prove that null hypothesis. Could the leopard spots and their chemical halos be explained by the ordinary, if clever, chemistry of a sterile planet? They explored every plausible abiotic avenue with diligence and intellectual honesty. One major possibility was temperature. Could heat have driven these reduction reactions? High-temperature hydrothermal fluids, perhaps from a nearby volcanic or impact-generated heat source, could carry reduced chemicals like hydrogen sulfide or ferrous iron. As these fluids percolated through the rock and cooled, they might precipitate iron sulfides and phosphates in localized spots or veins. This is a known geological process, but the geological context of Chihuahua Falls argued powerfully against it. The rock was a fine-grained sedimentary mudstone laid down in a calm lake bottom, not a hydrothermally altered fracture or vein. There was no evidence in the surrounding strata for the kind of intense, focused heat or the plumbing system required for sustained hydrothermal activity. Furthermore, the clay minerals within the rock itself are delicate indicators. They are altered or destroyed by sustained high temperatures. The very preservation of these pristine phyllosilicates testified to a low-temperature aqueous history, not a high-temperature hydrothermal one. The rock's nature quietly vetoed the idea of a hot origin. Another serious avenue of inquiry was the role of water chemistry, specifically acidity. The solubility, mobility, and reactivity of both iron and sulfur are highly dependent on the pH of the water. In highly acidic conditions, iron, the Frine ions, dissolve readily and can be reduced to iron the 5 through purely chemical reactions with other minerals or with simple organic matter, even without microbial catalysis. For example, ferric iron can be abiotically reduced by hydrogen sulfide gas, a process that can produce iron sulfide minerals. Perhaps The team reasoned the ancient waters of Jezero were more acidic than our models of a neutral lake suggested. A lower pH could create a chemical environment ripe for the abiotic formation of these mineral spots through simple inorganic redox reactions. This was a plausible and serious alternative hypothesis, one that had to be addressed with evidence, not dismissed by desire. And then perseverance itself provided a critical, almost poetic piece of counter-evidence that seemed to close this particular door. Nestled near the Chawa Falls sample site, the rover's cameras identified a small greenish rock fragment. Spectroscopy confirmed it. Olivine. Olivine is a magnesium-iron silicate, a mineral that forms in the fiery, reducing depths of a planetary mantle and is often carried to the surface in volcanic eruptions. It is a beautiful mineral, but it is also famously unstable in the presence of water, especially acidic water. Its crystalline structure is not held together by a strong covalently bonded network like the silica tetrahedra in quartz, but by ionic charges between isolated silicate tetrahedra and positively charged magnesium and iron ions. In an acidic environment, hydrogen ions from the water swarm the mineral surface, readily displacing these metal ions in a process called hydrolysis, breaking the olivine down rapidly into other minerals like serpentine and magnetite, a process that releases hydrogen gas. The persistence of recognizable, unaltered olivine grains in the immediate vicinity of the Chawa Falls mudstone is a powerful, almost silent witness. It testifies that the prevailing water chemistry during the rock's formation and subsequent diagenesis was not highly acidic. If it had been, the olivine would have been long since consumed. This pointed toward a neutral to mildly alkaline pH, precisely the pH range most conducive to the development and preservation of life as we understand it, and less conducive to many of the rapid abiotic ion reduction pathways. One by one, the leading non-biological explanations faced significant, often formidable, challenges from the data. The texture didn't match a high-temperature origin. The chemistry and mineralogy argued against a highly acidic environment that could drive rapid abiotic reduction. This does not, of course, constitute proof of a biological origin. In science, the absence of evidence for one hypothesis is not positive evidence for another. A yet unknown abiotic process, peculiar to the Martian environment, could conceivably produce such features. However, what this systematic elimination does is narrow the field of plausible explanations. It raises the burden of proof for any remaining abiotic hypothesis. When multiple independent lines of evidence, the specific mineralogy, graegit, potential vivianite, the distinctive chemistry, iron-phosphorus rims, the evocative texture, concentric spots, and the supportive geological context, a neutral pH lake sediment, all converge and consistently point toward a single remaining hypothesis. That hypothesis gains immense weight. It moves from the realm of idle speculation into the realm of a testable, high-value target, a candidate so compelling it demands further, more definitive investigation. The researchers concluded, with measured and professional gravity, that they could not, with the data from the rover alone, definitively rule out a biological origin for the features. This is a statement of profound scientific integrity and immense significance. It is not a claim of discovery. It is a declaration of compelling mystery. It is the raising of a flag on a distant shore, not of conquest, but of a promising landing site for future exploration. It signals that here, in this specific layer of ancient Martian mud, lies one of the most promising, most coherent candidates for a potential biosignature that humanity has ever laid its instruments upon, even if those instruments are robotic. The long and sobering history of Martian exploration, however, is a silent graveyard of raised flags that later fell, of hopes kindled and then carefully extinguished by further scrutiny. This context is not a dampener on excitement, but an essential source of wisdom, a necessary tempering of emotion with the hard-won lessons of experience. The ghost of past false positives haunts the corridors of every conference, the pages of every new paper claiming a potential biosignature. It is a ghost that reminds us of the universe's boundless capacity to surprise and deceive with its chemistry. The first and most famous of these ghosts is from 1976. The twin Viking landers, technological marvels of their age, touched down on Mars, carrying the first and to this day only dedicated life detection experiments ever sent to another world. Among their suite of instruments was the labeled release experiment, a masterpiece of elegant design. It scooped a small sample of Martian soil into a chamber and injected a nutrient broth rich in organic compounds, where the carbon atoms were the radioactive isotope carbon-14. The idea was straightforward. If living microbes were present in the soil, they would metabolize the nutrients and release carbon dioxide gas as a waste product. That carbon dioxide would contain the radioactive carbon-14, which a detector would sniff. To the astonishment and elation of the Viking biology team, the experiment registered a positive signal. The radioactive gas was released. For a heady moment, it seemed humanity had its answer. The front pages of newspapers proclaimed the discovery of life on Mars. But the triumph was agonizingly short-lived. The experiment's elegance was also its vulnerability. Subsequent experiments on Viking, particularly the gas chromatograph mass spectrometer, which searched for organic molecules in the soil directly, found none, a puzzling result, if life was present. The initial jubilation gave way to confusion, then to a growing consensus that the positive result was likely a chemical false positive. Decades later, the mystery found its most plausible solution with the 2008 discovery by the Phoenix lander. Martian soil is rich in perchlorates, salts containing chlorine and oxygen that are highly reactive oxidizing agents. When the Viking nutrients were added to the soil, these perchlorates could have reacted chemically with the organic compounds in the broth, breaking them down and releasing carbon dioxide through simple, sterile oxidation chemistry. A brilliant experiment was ultimately foiled by the unanticipated, exotic chemistry of an alien world. It was a humbling lesson. The universe can mimic the signs of life without the presence of life itself. Then, in 1996, a different kind of hope emerged, not from a lander on Mars, but from a rock that had traveled to us. Meteorite ALH 84001, a 4.1 billion-year-old piece of Martian crust that had been blasted into space by a colossal impact, spent millions of years in a lonely solar orbit before being captured by Earth's gravity and falling onto the Antarctic ice, was recovered in 1984. Over a decade later, a team of scientists made a stunning announcement. Under powerful scanning electron microscopes, they had revealed within carbonate globules in the meteorite tiny worm-like structures, some only 100 nanometers in diameter. They bore an uncanny resemblance to fossilized nanobacteria. The team also reported the presence of polycyclic aromatic hydrocarbons, PAHs, and mineral phases like magnetite grains in forms they argued were biogenic. The implications were so profound that President Bill Clinton stood on the White House lawn and addressed the world, speaking of the possibility that life once existed beyond Earth. The moment was a cultural landmark, a testament to the overwhelming power of the question. Yet, once again, time and the relentless engine of scientific scrutiny eroded the biological interpretation. The nanofossils were orders of magnitude smaller than any known cellular life, pushing the limits of the minimal possible size for a functional cell. Detailed geochemical work demonstrated that the carbonate globules and their included magnetite grains could be formed through non-biological mineral precipitation processes like templating, or through the abiotic process of serpentinization, where water reacts with olivine-rich rock. The PAHs, while organic, are common in the interstellar medium and could have been contaminants from the Antarctic ice or were inherent to the rock from non-biological processes. Another promising lead, announced with global fanfare, faded into the background noise of geological complexity, though it remains a seminal case study in the challenge of biosignature interpretation. These episodes are not failures of science. They are science in action. They are demonstrations of the self-correcting mechanism, the immune system of knowledge that prevents us from fooling ourselves for long. They teach a humbling, essential lesson: the universe is inventive beyond our imagination. Chemistry, under the right conditions of pressure, temperature, and concentration, can produce patterns, structures, and molecules that mock biology with cruel perfection. To distinguish the mockery from the real thing requires more than a single intriguing line of evidence. It requires a confluence, a consistency across multiple independent methods, and ultimately a level of analytical depth that, for a discovery of this ultimate magnitude, can likely only be achieved in the sophisticated, bulky, and powerful laboratories of Earth. This is the crucible through which the Chawa Falls sample, now sealed in a tube named Sapphire Canyon, must pass. The specters of Viking and ALHE 4001 are precisely why the team behind the Perseverance discovery speaks with measured caution. Why NASA's announcements are couched in the language of potential and promise rather than proclamation. We have been intellectually burned before, and those burns leave scars of wisdom, teaching us to look more deeply, to question more thoroughly, to demand a higher standard of proof. And so, the question hangs in the thin, cold Martian air. More poignant now than ever is the Chawa Falls mudstone, the long-awaited third time's charm, the moment when the signal finally breaks through the noise. Or is it merely the latest and most sophisticated chapter in a long storied history of cosmic tease, a Martian siren song that will fade upon closer inspection? To settle this question, to move from compelling candidate to confirmed discovery, we must achieve an ambition that has been the holy grail of planetary science for decades. We must bring a piece of Mars home. The mission architecture is known as Mars Sample Return, and it is arguably the most complex, choreographed robotic space mission ever conceived. It is an interplanetary ballet requiring perfect timing and execution across years and hundreds of millions of kilometers. A relay race with a baton passed between robots in deep space. Perseverance is the indispensable first act. It is not just an explorer, it is a prospector and a curator. Its drill, a rotary percussive marvel, has extracted cylindrical core samples from Chiawa Falls and other compelling sites, each about the size of a piece of classroom chalk. These cores are sealed within ultraclean, hermetically sealed tubes of titanium, engineered to preserve their pristine state and protect them from contamination for the decades-long journey ahead. One of these tubes, containing the precious mudstone with its enigmatic leopard spots and poppy seeds, has been given the evocative name Sapphire Canyon. These tubes are now being carefully deposited at designated cache sites on the Martian surface, a treasure map with an X marked in regolith, waiting for a future mission to retrieve them. The second act is a feat of engineering that will make Perseverance's landing look almost routine. A new spacecraft, a sample retrieval lander, would be sent from Earth. This lander, larger and more capable than any before, would carry with it a small fleet of auxiliary vehicles. The current concept envisions two key components: a fetch rover, perhaps built by the European Space Agency, to navigate autonomously to the cache site, locate and collect the sample tubes, and return them to the lander platform, and a Mars ascent vehicle, a small two-stage solid-fuel rocket that would stand on the red soil, the first human-built vehicle ever to await launch from another world. Imagine the scene on a silent plain, under a pink sky. This slender rocket, containing within its payload fairing the most precious cargo ever collected by our species, rocks that may hold the answer to life's cosmic solitude, ignites its engines. It lifts off in a silent burst of flame, for sound requires a medium, and the Martian atmosphere is too thin to carry much, ascending on a pillar of fire, leaving behind only a scorch mark and the empty lander. It is a moment of pure, transcendent ambition, a declaration that we can not only reach other worlds, but return from them with their secrets. This ascent vehicle would then need to place the sample container, a basketball-sized orb, into a stable orbit around Mars. Precision is everything. A miscalculation could send the samples hurtling into the Martian atmosphere to burn up, or drifting into solar orbit, lost forever. Into this orbital arena enters the third and final actor, the Earth Return Orbiter, another likely contribution from international partners. This spacecraft, having journeyed from Earth and entered orbit around Mars, would have to perform a delicate robotic rendezvous. It would locate the orbiting sample, match its trajectory, and capture it using a sophisticated mechanism, perhaps a robotic arm or a containment system that swallows the orb whole. Once secured, the Earth Return Orbiter would fire its engines, breaking free of Mars's gravity to begin the long, silent voyage home. Upon approaching Earth, it would release the sample capsule on a precise trajectory. This capsule, a blunt-nosed, heat-shielded vessel, would then slam into Earth's atmosphere at hypervelocity over 25,000 miles per hour, enduring temperatures hotter than the surface of the Sun as it breaks. A parachute system would deploy, and the capsule would drift down to a designated, secure landing zone, likely a military range or a remote desert, to be recovered by teams in biological containment suits. The entire endeavor is a chain of unprecedented technological feats: autonomous rendezvous and capture in deep space, launch from another planet, precision atmospheric re-entry, each link with near-zero margin for error. Its projected cost, in the realm of $11 billion or more, reflects its staggering ambition and complexity. And its timeline, once hopeful for the early 2030s, has been pushed back by budgetary constraints technical challenges, and programmatic reassessments, with some estimates now pointing to the 2040s or even later. This delay persists despite Mars sample return being crowned the highest priority flagship mission for NASA by the planetary science community for 2 consecutive decades. The discovery at Jezero Crater adds an almost unbearable poignancy and urgency to this delay. The potential biosignature now physically exists, locked in a titanium tube on another world, waiting. The samples are there, the will, the funding, the political and societal resolve to retrieve them is the next great non-scientific hurdle in this cosmic quest. It is a test of our species' commitment to answering the great questions, not just for this generation, but for all those to come. Should that will be mustered, the funding secured, the engineering challenges overcome, and the samples successfully delivered to a sterile laboratory on Earth. What then? What alchemy, what profound interrogation will our scientists perform upon these fragments of another world? The laboratories that will receive them are not yet fully built, but they are being designed with a level of biocontainment and cleanliness exceeding that used for the most dangerous pathogens on Earth. Facility Risk Group 4, agents like Ebola virus. This is not out of fear that Martian life might be hazardous. The consensus is that any Martian organisms, if they exist, would be so alien to Earth's biochemistry as to be incapable of interacting with our biology and likely long dead. The extreme containment, termed break-the-chain protocol, is to protect the samples from terrestrial contamination. A single terrestrial bacterium or stray human skin cell introduced into the analysis could confound the results, creating a false positive that would destroy the scientific value of the sample. Therefore, the samples will be handled in glove boxes under a continuous purge of ultra-filtered inert gas by scientists working through sealed ports, using tools sterilized at extreme temperatures. The samples themselves may be baked at low temperatures under vacuum to vaporize any potential terrestrial contaminants on their exterior before the tubes are opened. Within these pristine, cathedral-like cleanrooms, scientists will deploy an arsenal of analytical techniques far more powerful, precise, and bulky than anything that can be miniaturized and sent to Mars on a rover. They will use microtomes with diamond knives to slice the rock into sections thinner than a human hair, creating wafers for transmission electron microscopy. They will deploy synchrotron light sources, particle accelerators that produce incredibly intense, focused beams of X-rays to map the sample's elemental and molecular composition in 3 dimensions with nanometer-scale resolution, visualizing the intimate relationships between minerals and any potential organic remains. They will use secondary ion mass spectrometry, SIMS and nano-SIMS instruments, which fire beams of ions to sputter away atoms layer by layer, measuring their masses with incredible precision to map isotopic ratios at the microscale. This isotopic analysis is one of the most promising lines of inquiry. Carbon atoms, for instance, come in stable forms with different masses, carbon-12, with 6 protons and 6 neutrons, and carbon-13, with 6 protons and 7 neutrons. Life, in its biochemical processes, photosynthesis, methanogenesis, other forms of carbon fixation, exhibits a distinct preference, or fractionation, for the lighter carbon-12 isotope. This is because the enzymatic reactions that build organic molecules work slightly more efficiently with the lighter atom, requiring less energy to move and incorporate. Thus, living matter on Earth consistently has a higher ratio of carbon-12 to carbon-13 than the inorganic carbon found in carbonate rocks or the atmosphere. It leaves a signature, a skew in the numbers. If the organic carbon within the Sapphire Canyon sample shows a similarly skewed isotopic ratio depleted in carbon-13 relative to the surrounding inorganic matrix, it would be a powerful, though still not absolutely conclusive, indicator of biological processing. It would suggest that a selective enzymatic process was at work, not just random organic synthesis. Another profound and potentially definitive line of inquiry will examine chirality or molecular handedness. Many organic molecules, particularly the amino acids that are the building blocks of proteins and other key biological polymers, exist in two mirror image forms, like a left and a right hand. They are chemically identical in most respects. Same atoms, same bonds, but their three-dimensional spatial arrangement is opposite, and they cannot be superimposed, just as a left glove does not fit a right hand. In the non-living world, chemical reactions such as those simulated in the famous Miller-Urey experiment, or those occurring in interstellar ice mantles, tend to produce a racemic mixture, a roughly 50-50th split of left-handed and right-handed versions. Life, however, is homochiral. All known life on Earth uses exclusively left-handed amino acids, L-amino acids, to build its proteins, and right-handed sugars, D-ribose and D-deoxyribose, in its nucleic acids, DNA and RNA. No one knows for certain why this profound preference exists. It may be a frozen accident of early biochemistry that, once established, became locked in because polymers built from a single chirality fold and function more efficiently. But its near universality in terrestrial biology makes it a hallmark, a signature of a system that selectively incorporates one form over the other, a process intimately tied to self-replication and metabolism. If detailed analysis of amino acids or other chiral molecules in the Martian sample reveals a strong, overwhelming dominance of one chiral form over the other, whether it is left or right-handed, it would be one of the most compelling smoking gun biosignatures imaginable. It would be extremely difficult to explain such a pure homochirality through any known abiotic process. It would point decisively toward a system that had the capacity for selection and templated replication. Recognizing that the interpretation of biosignatures is a nuanced, graded, and often contentious endeavor, not a simple binary yes or no, NASA and the scientific community have developed a formal framework called the Confidence of Life Detection Scale, or COLD scale. It consists of 7 levels, a ladder of certainty that a discovery must climb, with each step requiring stronger, more independent evidence. Level 1 is the initial detection of a signal that could be indicative of life, but could also be abiotic. This is where many discoveries start. Level 2 involves ruling out contamination from the spacecraft itself, ensuring the signal is from Mars. Level 3 demonstrates that the signal is indigenous to the Martian environment, not a meteorite from elsewhere. Level 4 is the rigorous work of ruling out all known abiotic explanations for the signal, which is precisely the work the Perseverance team has begun with Chihuahua Falls. Level 5 requires the identification of complementary, independent biosignatures within the same sample, for example, finding both morphological features like cells and a supportive chemical isotopic signature. Level 6 is independent confirmation of the findings by other instruments or teams, likely requiring the sample return and analysis in multiple Earth labs. Level 7, the pinnacle of certainty, would involve making follow-up observations, such as finding similar compelling evidence in a different unrelated location on Mars, showing it is not a one-off anomaly. The discovery at Jezero crater, as it stands from the rover data alone, likely resides somewhere between levels 3 and 4. It is a signal that is indigenous and compelling, with leading non-biological explanations facing significant hurdles. To climb to level 6 or 7 is the work of a generation, requiring the successful sample return, years of painstaking analysis, and potentially follow-up missions to other sites. This graduated scale is a testament to the scientific maturity of the search. It acknowledges that discovery is a process, a journey of accumulating evidence and consensus, not a single dramatic event. Let us, for a breathtaking moment, engage in the grandest of speculations. Let us imagine that the political and financial stars align, that the Mars sample return mission is funded, built, and executed flawlessly, that in the 2040s, a capsule lands in the Utah desert, is secured, and transported to the waiting biocontainment facility. Let us imagine that over the ensuing years, the most advanced analytical techniques are brought to bear on the Sapphire Canyon sample, that the isotopic analyses show a pronounced carbon-12 enrichment in the organic matter, that chiral analysis reveals a pure homochirality in amino acids, that nanoscale imaging reveals structures consistent with cell walls or microfossils within the leopard spots correlated perfectly with the iron-phosphorus rims, that after a decade of the most intense, skeptical global scrutiny, a scientific consensus slowly, inexorably forms. Life once existed in the Jezero crater lake. Not a contaminant, not an abiotic mimic, but a bona fide ancient Martian biota. What then? The immediate scientific implications would be staggering, rewriting textbooks overnight. It would confirm that Mars was not only habitable, but was indeed inhabited. The specific age of the sediment, determined by isotopic dating techniques possible only on Earth, would tell us for how long this biological window remained open, potentially pushing the era of a living Mars further forward in time than currently believed. The nature of the metabolisms inferred, iron reduction, sulfate reduction, would paint a picture of an anoxic chemosynthetic ecosystem, possibly subsurface influenced, thriving in the lake sediments. It would provide a comparative data point for understanding the early evolution of life on Earth, suggesting that such metal-based metabolisms are a common, perhaps even necessary, stepping stone in planetary biospheres. But the philosophical, existential, and cultural ramifications would eclipse even the scientific ones, sending tremors through every foundation of human thought. We would have our second data point in the grand equation of life in the universe. We would know, with empirical certainty, that the phenomenon of biogenesis, the transition from non-life to life, is not a unique, miraculous property of Earth. The universe, in at least one other location, under a different sky, crossed that sacred threshold from inert chemistry to living, metabolizing, evolving biology. This single piece of knowledge would instantly and irrevocably transform the Drake equation, The famous probabilistic framework devised by astronomer Frank Drake to estimate the number of communicative civilizations in our Milky Way galaxy. The equation is a chain of multiplying factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per star system, and then the critical pivotal factor of underscore, the fraction of those habitable planets on which life actually emerges. For decades, this value has been the great unknown, a placeholder representing our profound ignorance. It could be infinitesimally small, 1 in a trillion, making life on Earth a cosmic fluke, a statistical miracle in a barren universe. Or it could be close to 1, implying that life emerges as a natural, almost inevitable consequence on any world that provides liquid water, chemical energy, and a stew of essential elements for a long enough period. The discovery of an independent origin of life on Mars would be a direct measurement of S_L for our own solar system. If it happened independently on 2 neighboring rocky planets orbiting the same star, then the process is clearly not infinitesimally small. It suggests F_L is significant. The product of the Drake equation would therefore skyrocket, suggesting that the galaxy may be teeming not just with planets, but with life-bearing worlds. The cosmos would shift from a silent, sterile expanse to a potentially humming, living network. However, a critical and fascinating caveat exists, one that would immediately become the focus of intense research. This uplifting conclusion holds true only if Martian life represents a truly independent second genesis. There is another possibility, equally profound but statistically different: panspermia. This is the theory that life, or its precursor molecules, can be transported between worlds, encased in the protective interiors of rocks blasted off planetary surfaces by asteroid or comet impacts. Calculations show that numerous Martian meteorites have landed on Earth, and surely many Earth rocks have landed on Mars, especially during the late heavy bombardment period over 4 billion years ago, when impacts were frequent and violent. It is entirely possible that life arose first on Mars, perhaps earlier than on Earth due to its faster cooling, and was carried to Earth via meteorite, seeding our planet. Or vice versa, life arose on Earth and was transported to Mars. In this scenario, Earth and Mars would not represent 2 independent origins, but 2 branches of a single family tree, a single genesis event that spread across 2 worlds. This would still be a monumental discovery, proof that life can survive the rigors of interplanetary ejection, space travel, and re-entry, that a biosphere can seed new worlds. It would mean life, once started, is resilient and can spread through a star system. But it would leave the value of N_L, the probability of that initial spark, still unknown. Was that first genesis on Earth or Mars a rare singular miracle, or is it a common event? We would only have one example of the origin event itself. Distinguishing between these 2 scenarios, independent genesis versus panspermia, would instantly become the next great scientific frontier. We would search for a fundamental biochemical divergence. Does Martian life use the same genetic code, the same mapping of nucleotide triplets to specific amino acids? Does it use the same set of 20 canonical amino acids, or a different subset? Most tellingly, what is its chirality? If Martian life uses right-handed amino acids, it would be powerful evidence for a separate origin, as it would indicate a different frozen accident. If it uses the same left-handed amino acids as Earth life, panspermia becomes a compelling, though not definitive, explanation. The detective work would move to the molecular level, comparing the deep architecture of two potential biologies. This line of thinking leads us to a profound philosophical and statistical principle often invoked in discussions of astrobiology and cosmology: the zero-Bato rule, articulated in various forms by thinkers like Arthur C. Clarke and others. It posits that, in a logical and statistical sense, life can only exist in 0, 1, or an infinite number of places in the universe. 0 we have already ruled out by our own existence. We are here. 1 is the lonely Earth hypothesis, where we are a singular, freakish accident. But if we find life in a second place, Mars, then the leap from 1 to 2 is, in a cosmic sense, a leap from 1 to infinity. The reasoning is statistical. If life has arisen independently twice in the same solar system, a single, unremarkable corner of a galaxy of hundreds of billions of stars, then there is no logical, statistical, or physical reason it would not have arisen countless times across the galaxy and the universe. The discovery of a second genesis in our backyard would strongly imply that the universe is in fact biophilic, that its laws and conditions are such that life emerges naturally and commonly wherever the conditions are right. The psychological and philosophical shift for humanity would be tectonic, on par with the Copernican revolution or Darwin's theory of evolution. We would cease to be a singular miracle, a fragile spark in an endless night, and would become a natural part of a living, perhaps even a conscious, cosmos. The Earth would be demoted from a unique sanctuary, a special creation, to a single specimen in a vast biological gallery, one tree in a cosmic forest. For some, this is a terrifying prospect, invoking a sense of existential vertigo, a loss of specialness and cosmic purpose. For others, it is the ultimate liberation, a sign that we are woven into the fabric of a creative, fecund, and inherently meaningful universe. It could fundamentally reshape human identity, our art, our literature, our philosophy, our very sense of purpose and place. Would such a discovery unite humanity as we see ourselves, not as tribes or nations, but as a single, fortunate species that has discovered it has cosmic cousins, shifting our gaze outward in common cause? Or would it deepen our existential anxieties, making our individual lives seem even more insignificant against a backdrop of a galaxy brimming with life? History suggests that great discoveries about our place in the cosmos, the heliocentric model displacing Earth from the center, the revelation of galaxies beyond our own showing the Milky Way, was not the universe, were initially destabilizing, challenging dogma and identity, but ultimately they were enlightening, expanding the human mind to accommodate a larger, grander, and more wonderful reality. Yet, even in the face of this breathtaking potential, we must hold in careful balance the other, equally important and statistically possible outcome. What if, after all this effort, the returned Sapphire Canyon sample reveals no definitive signs of past life? What if the most sophisticated Earth-based analyses conclude that the leopard spots are the product of an exotic, abiotic chemistry we simply had not yet fully comprehended, a Martian geochemical pathway that mimics biology with uncanny precision? Would the Mars sample return mission then be a failure? Would the hope have been for naught? Not in the slightest. It would be a discovery of a different kind, but one of immense and enduring scientific value. We must remember that Mars, in its frozen geological state, is a pristine time capsule of the early solar system. Earth's surface is a dynamic, restless palimpsest, constantly rewritten by the relentless engines of plate tectonics, erosion, volcanism, and most pervasively, biological activity. The rocks from our own planet's first billion years, the Hadean and early Archean eons, are almost entirely obliterated, recycled into the mantle or metamorphosed beyond recognition. We have only a handful of tiny altered zircon crystals and a few highly metamorphosed rock sequences to tell that story. Mars, lacking active plate tectonics for most of its history, has preserved its ancient crust like a museum. Its surface geology from 3.5 to 4 billion years ago is exposed, accessible, and relatively unaltered. By studying the Jezero crater sediments in exquisite detail, even if they are conclusively sterile, we are looking at a snapshot of what a wet, rocky planet looks like before life, or in the absence of life, transforms it utterly. We are seeing the chemical and sedimentological context in which life might have arisen, the abiotic baseline. This provides the essential control sample, the null condition that is missing from Earth's record. On Earth, we cannot easily disentangle what features of our ancient rocks are purely geological and which are biological, because biology has reworked the planet so thoroughly. Mars offers a pristine laboratory of prebiotic or non-biotic planetary evolution. Understanding this abiotic baseline is not a side quest. It is crucial for recognizing true biosignatures elsewhere, both in our solar system and on exoplanets. Furthermore, the complex organic molecules themselves, even if not forged by biology, would be of profound interest. How did they form? Were they delivered by comets and asteroids, or synthesized in the Martian atmosphere via photochemistry, or formed in the sediments through geochemical reactions like Fischer-Tropsch type synthesis? They could provide vital clues to the chemical steps that led to life on Earth, steps whose record is lost in our own planet's turbulent history. The Martian samples would be a Rosetta Stone for prebiotic chemistry. So, the Mars sample return endeavor is, in a very real sense, a win-win proposition for science. Either it reveals a second Genesis, revolutionizing our understanding of life and our place in the cosmos, or it provides an unparalleled, pristine window into our own prebiotic past, the chemical runway before the takeoff of life. The quest, therefore, is not a high-stakes gamble on a single binary outcome. It is a guaranteed, monumental expansion of human knowledge into realms we have never before been able to touch directly. But the story of the search for life on Mars, and indeed in the universe, does not begin or end with the ancient surface sediments of Jezero crater. Perseverance's mission is strategically focused on the search for ancient surface life. Life that flourished billions of years ago when the surface was clement and wet. This is a logical, evidence-based strategy, given what we know of Mars's climatic history. The surface today is a harsh, radiation-blasted desert. Ultraviolet light from the sun, unfiltered by a thick ozone layer, sterilizes the top layers of soil. Cosmic rays, high-energy particles from across the galaxy, penetrate meters deep, breaking apart complex molecules. The atmosphere is too thin and cold for liquid water to persist for more than brief moments in certain conditions. It is, by any measure, profoundly inhospitable to life as we know it on its surface. However, our very concept of habitability has undergone a radical paradigm-shifting expansion in recent decades. A revolution fueled not by looking outward, but by looking downward, right here on Earth. We have learned that life is not merely or even primarily a surface-dwelling phenomenon. It is a planetary-scale process that has penetrated astonishingly deep into the crust, into realms of darkness, pressure, and chemistry we once thought sterile. This is the realm of the deep biosphere, a vast, slow-motion, and largely unexplored ecosystem that exists in near total independence from the sunlit world above. On Earth, microbial life, bacteria and archaea, has been found thriving kilometers below the seafloor in ancient ocean sediments, and deep in the fractured bedrock of continents, surviving at tremendous pressures and temperatures that can exceed 120 degrees Celsius. These organisms, known collectively as extremophiles, or more specifically for subsurface dwellers, endoliths or SLIMs, subsurface litho-autotrophic microbial ecosystems, derive their energy not from photosynthesis but from chemosynthesis. They harness the chemical energy released from reactions between water and rocks. For example, they can oxidize hydrogen gas produced when water reacts with iron-rich minerals like olivine in a process called serpentinization. Or they can reduce sulfate or carbon dioxide using hydrogen or other electron donors. The total biomass of this hidden subsurface realm is staggering. Some estimates suggest it may rival or even exceed the biomass of all life on the surface, from the depths of the oceans to the rainforest canopies. These discoveries have fundamentally rewritten the rules of where life can exist. This revolution in understanding fundamentally alters the astrobiological equation for Mars and indeed for all rocky worlds. While Mars's surface may have died over 3 billion years ago, its interior is not dead. Heat is still generated by the decay of radioactive isotopes of potassium, thorium, and uranium in the core and mantle. This provides a gentle, persistent geothermal gradient. There is overwhelming evidence from orbital radar and neutron spectrometers for widespread subsurface water ice, a global cryosphere. And where residual geothermal heat meets this ice, there is the potential for liquid water brines to exist in porous rocks or in fractures, forming deep, isolated aquifers. These subsurface environments would be perfectly shielded from the lethal radiation and extreme temperature swings of the surface. They could provide a stable, if austere and energy-limited, refuge for life. This opens two profound possibilities. First, life that originated on the surface during the wet, early epoch could have retreated underground as the climate deteriorated, following the retreating water table into the deep crust, surviving in isolated pockets for billions of years up to the present day. Second, it is even possible that life originated in the subsurface, in hydrothermal systems driven by volcanic or impact heat, powered solely by chemosynthesis, never seeing the light of the sun. Mars, with its evidence of past volcanism and its likely residual heat, could have harbored such a deep biosphere in the past, or may still harbor it today. The mysterious, intermittent detections of methane in the Martian atmosphere by the Curiosity rover and from orbit add a tantalizing layer of intrigue to this possibility. On Earth, a significant portion of atmospheric methane is biologically produced by methanogenic archaea in wetlands, guts of animals, and the subsurface. Methane can also be produced abiotically through geochemical processes like serpentinization. The Martian detections have shown puzzling seasonal variations and occasional plumes. While abiotic explanations remain viable, the variability is intriguing because on Earth, biological activity often follows seasonal cycles. Some scientists cautiously interpret these observations as potentially consistent with a subsurface biological source, a population of methanogenic microbes slowly metabolizing in damp, warm fractures, producing methane that episodically diffuses or is vented to the surface. It is a hint, nothing more, but a hint that points downward. If a deep, surviving biosphere does exist on Mars, it would likely be microbial, incredibly slow metabolizing, with potential generation times of centuries or millennia, and dispersed in isolated niches. Finding it with our current technology would be a monumental challenge. Our surface rovers can drill only a few centimeters into rock. Reaching potential aquifers or hydrothermal zones kilometers below would require a new class of mission, dedicated deep drilling landers, perhaps using nuclear-powered or laser-heated drills, capable of penetrating hundreds of meters or more. It is a daunting engineering problem, but the scientific payoff would be beyond compare. It would mean that life is not a relic on Mars, but a contemporary resident. It would demonstrate life's incredible tenacity, its ability to cling to existence in a planet's last hospitable niches for billions of years after its surface world died, a testament to the conservatism of biology once it gains a foothold. This prospect subtly shifts the most likely address for extant Martian life from the ancient lake beds now being explored to the deep, dark, warm fractures in the crust, places like the subsurface beneath the vast Tharsis volcanic province or the large, ancient impact basins that may have triggered long-lived hydrothermal systems. Our current surface-focused strategy, for all its brilliance, may be, quite literally, only scratching the surface of Mars's full biological potential, past and present. The search for life beyond Earth, of course, extends far beyond the rust-colored plains and hidden depths of Mars. Our solar system, we now know, is a diverse archipelago of worlds, many of which hold tantalizing prospects for habitability in forms we are just beginning to understand. Chief among these are the icy moons of the giant planets, worlds where the conditions for life may exist not on the surface but beneath it, in global oceans sealed under frozen shells. Jupiter's moon Europa, slightly smaller than Earth's moon, is the archetype. Data from the Galileo spacecraft and telescopic observations strongly suggest it harbors a global saltwater ocean, perhaps 100 kilometers deep, locked beneath an icy crust estimated to be tens of kilometers thick. This ocean is kept liquid not by the faint warmth of the distant sun, but by tidal heating, the gravitational flexing of the moon's interior as it orbits Jupiter in an eccentric orbit, squeezed and stretched by the giant planet's immense gravity. This internal heat source is powerful and persistent. At the seafloor of Europa, where the liquid water meets the rocky mantle, there could very well be hydrothermal vent systems, analogous to the Lost City or black smoke vents on Earth's mid-ocean ridges. These environments, rich in chemical energy and mineral nutrients, are oases for vibrant chemosynthetic ecosystems on our planet, independent of sunlight. They are considered prime candidates for where life could originate and thrive on Europa. Saturn's small, dazzling moon Enceladus presents an even more compelling and accessible case. Through the visionary discoveries of the Cassini spacecraft, we learned that Enceladus, though only 500 kilometers in diameter, is geologically active. Fractures near its south pole, dubbed tiger stripes, spew towering geysers of water vapor, ice crystals, salts, and organic molecules into space. Cassini famously flew through these plumes, sampling them directly with its mass spectrometer. The analysis revealed a startlingly complex chemistry: water vapor, sodium and potassium salts, silica nanoparticles, which on Earth are a signature of hot water interacting with rock, and a variety of organic molecules, including methane, propane, acetylene, and even hints of more complex macromolecular carbon. Most significantly, it detected molecular hydrogen in the plumes. Molecular hydrogen is a potent chemical energy source. On Earth, at hydrothermal vents, microbes use hydrogen as an electron donor to reduce carbon dioxide, a process called methanogenesis or acetogenesis, forming the base of the food web. The presence of molecular hydrogen, silica, and organics together strongly points to ongoing hydrothermal activity on the seafloor of Enceladus, where hot water is interacting with a rocky core. Enceladus offers a staggering gift: a free sample of its subsurface ocean delivered into space, where a spacecraft can intercept it. A future mission, an orbiter or a flyby craft with more advanced instruments, could analyze these plumes for amino acids, fatty acids, and even potential isotopic biosignatures, directly searching for the chemical fingerprints of life without ever landing or drilling. Further out, in the deep cold of the Saturnian system, lies Titan, a world that presents an entirely different, almost science-fictional paradigm for habitability. Titan is larger than the planet Mercury and shrouded in a thick, hazy, nitrogen-rich atmosphere. It is the only moon in the solar system with a substantial atmosphere and the only other world besides Earth with stable bodies of liquid on its surface. But these are not water lakes. On Titan, with surface temperatures around -180 degrees Celsius, water is frozen as hard as granite. The liquids are hydrocarbons, methane and ethane, which exist in liquid form at these cryogenic temperatures. Titan has rivers that carve meandering channels, lakes that fill deep basins, and even probable rainstorms of liquid methane. This challenges our profoundly water-centric definition of life. All known life on Earth requires liquid water as a solvent, a medium in which biochemical reactions can occur. Could there exist a form of life with a fundamentally different biochemistry that uses liquid methane or ethane as its solvent? Such hypothetical biochemistries, often discussed in the realm of astrobiology, force us to expand our imagination beyond terrestrial chauvinism. Titan's atmosphere is a factory for complex organic chemistry. Solar ultraviolet radiation and cosmic rays break apart methane and nitrogen high in the atmosphere, leading to a cascade of reactions that produce a rich soup of organic molecules: ethane, acetylene, hydrogen cyanide, and more. These molecules combine to form tholins, complex organic polymers that give Titan its orange haze and rain down on the surface, accumulating into dunes and potentially dissolving in the methane lakes. In the cold, dark lakes, or in hypothetical subsurface reservoirs of warmer water ammonia mixtures, these tholins could engage in chemical processes we can scarcely imagine, perhaps even leading to a form of metabolism based on the hydrogenation and dehydrogenation of hydrocarbons. While finding water-based life, as we know it on Titan, is unlikely, the discovery of a truly alien form of life, a second Genesis, with a different foundational solvent and chemistry, would be an even more profound revolution in biology. It would tell us that life is not just a phenomenon of Earth-like, water-based conditions, but a truly universal principle of complex chemistry that can manifest in multiple diverse ways depending on the environment. Titan is a natural laboratory for testing the limits of this principle. As we peer beyond our own solar system to the thousands of exoplanets now confirmed to orbit other stars, the search for life enters a new, purely observational phase. We will not be sending rovers or landers to these distant worlds for centuries, if ever. The distances are too vast. A voyage to even the nearest star system, Proxima Centauri, with current technology would take tens of thousands of years. Therefore, our search must be conducted remotely by analyzing the faint photons that reach us across the light years. The next generation of space telescopes, such as the Habitable Worlds Observatory, currently in its early planning stages at NASA, will be designed with this explicit goal. Its aim will be to directly image Earth-sized planets in the habitable zones of Sun-like stars. This is a monumental technical challenge. A planet orbiting a star is like a firefly next to a searchlight. The star is billions of times brighter. To see the planet, we must physically block out the star's light using an instrument called a starshade or a coronagraph, an occulter that flies in formation with the telescope to create an artificial eclipse. Once we have a pale blue, or perhaps pale green or pale red dot in our sights, we will deploy the powerful technique of spectroscopy. By collecting the faint starlight that has filtered through the planet's atmosphere during a transit or that is reflected from its day side, and then spreading that light into a spectrum. A rainbow crossed with dark and bright lines, we can identify the chemical fingerprints of gases and surfaces. This is how we know the atmospheres of hot Jupiters contain water vapor, sodium, and other elements. For an Earth-like exoplanet, we will search for biosignature gases, not just a single gas like oxygen, which can be produced abiotically in certain circumstances. For example, by the photodissociation of water vapor on a planet without life, but combinations of gases in chemical disequilibrium. For instance, the simultaneous presence of significant amounts of methane and oxygen in an atmosphere is hard to maintain without a continuous biological source, as they react rapidly with each other to form carbon dioxide and water. Finding both together would be a powerful indicator. We might also look for the red edge of vegetation on Earth. Chlorophyll in plants strongly reflects near-infrared light while absorbing visible red light, causing a sharp jump in reflectivity at about 700 nanometers. An exoplanet with a similar spectral feature might indicate the presence of photosynthetic pigments, though they would likely be adapted to the light of their host star, which could be redder or bluer than our Sun. We might even search for technosignatures, signs of technology and intelligence. These could include artificial lights on the night side of the planet, unusual industrial pollutants like chlorofluorocarbons or nitrogen oxides in the atmosphere, or even the leakage of radio or laser signals. The detection of any such sign, however faint, would answer not just the question of whether life exists elsewhere, but whether intelligence, civilization, and perhaps consciousness are also cosmic phenomena. It would tell us that the universe not only gives rise to life, but to minds that can look back and wonder. This grand, multi-generational quest stretching from the mudstones of Jezero crater to the atmospheres of exoplanets 1,000 light-years away is driven by something more fundamental than curiosity. It is driven by a deep, intrinsic human yearning to understand our context, to know our place in the great story. Are we a lonely accident in a silent, mechanical, and ultimately meaningless universe, a fleeting anomaly of complex chemistry destined to fade without echo? Or are we part of a vast, interconnected, and potentially infinite tapestry of living worlds? A cosmic story still in its early chapters, with wonders and revelations beyond our current imagination. The discovery of even a single fossilized microbe on Mars would irrevocably, definitively shift the answer toward the latter. It would provide concrete evidence that the universe is not just capable of creating stars and galaxies, of weaving the fabric of space-time, but of weaving that fabric into self-aware beings. It would mean that the laws of physics and chemistry are not barren but fecund, inclined toward the emergence of complexity, life, and perhaps mind. This knowledge, should we attain it, carries with it a profound responsibility, a new ethical dimension to our existence. If life is common, then its preservation on our own fragile world and potentially on others we encounter becomes a sacred duty. The existing ethical framework of planetary protection, the guidelines to prevent the forward contamination of other worlds with Earth life and the back contamination of Earth with potential extraterrestrial life, would take on new urgency and moral weight. We would have to view ourselves not just as explorers or colonists, but as stewards, as representatives of a biological brotherhood that may span the galaxy, tasked with preserving the miracle of life in all its forms, wherever we find it. As we stand on this precipice of potential discovery, let us return in the mind's eye to the quiet desolation of Jezero crater. The Martian sun, a pale, small disk in a pink sky tinged with dust, dips toward the crater's western rim. Long, cold shadows stretch across the ancient delta, its layered cliffs painted in hues of gold and rust by the slanting light. The Perseverance rover sits beside its cached treasure, a silent, metallic sentinel in the gathering dusk. Its solar panels angled toward the dying light, storing energy for another day of patient work. The wind, that eternal whisper, picks up slightly, moving from the highlands toward the lowlands as it has for eons. It scours the rocks, smoothing edges, carrying away the finest dust, slowly, imperceptibly erasing the tracks of the robotic visitor, just as it has erased the shorelines of the ancient lake. In the deepening cold, the silence reasserts itself, a physical presence once more. But within one of those sealed tubes, within the sample named Sapphire Canyon, a secret endures. It is a secret written not in language, but in the silent alphabet of atomic relationships, in the bonds between iron and phosphorus, in the rings of carbon atoms, in the concentric halos of mineral spots. It is a message in a bottle, but the bottle is stone, and the message is written in chemistry. It was cast upon the shore of time over 4 billion years ago, when this place was not a desert but a lakefront, when the wind may have carried the scent of water, not dust. We have, across the gulf of space and with immense effort, found the bottle. We are now, with the finest tools of our intellect and technology, laboring to decipher the script. The message may tell us that we were never alone, that in its youth the solar system hummed with life in more than one locale. Or it may tell us that the universe is vaster and more mysterious than we ever dreamed, that the story of life's origin is a puzzle with its pieces still scattered across the cosmos, waiting to be found on other worlds around other stars. Either way, the act of searching, of reaching out with our machines and our minds across the void, is itself a testament to life's most beautiful and defining attribute, its relentless, insatiable curiosity. We are the universe becoming aware of itself, a collection of atoms forged in stellar furnaces, now able to contemplate its own origin and destiny. And in searching for other sparks of awareness, other nodes of contemplation in the cosmic dark, we complete a profound circle. We stare into the cosmic night, not with fear of the void, but with a hopeful, persistent question etched into our very being. And perhaps, in the faint chemical whisper from an ancient mudstone on a distant, rust-colored world, in the pattern of leopard spots and poppy seeds, we are, for the first time in our long history of wondering, beginning to hear the faint, tantalizing echo of an answer. Good night.